All right, so today let's try to finish the Jordan decomposition. Okay, so we're hopefully finally finishing it today. So remember what we're trying to prove? We're trying to prove that for any matrix A, it's a square, we can write it as a sum of blocks, which let's call J1, J2, like that. And we want to show that each of these blocks, these diagonal blocks, is a square matrix that looks like this. It's got some numbers that's diagonal on the super diagonal. Okay, that's the goal. All right, so remember, it's a very theoretical decomposition, but it's very important to understand how dynamical systems behave. So it's of course, our machines are dynamical systems, so we have to study them. Okay. So in the last class, effectively what we showed is that after going to the Schur decomposition, lots of calculation, we could reduce the matrix by some change of variable to blocks that look like this, where each R was just an upper triangular matrix with constants on the diagonal, right? That's how far we came. And then we said, so it's enough in the proof to show that each of these blocks can be written like this, and then we'll be done, right? So the proof was, okay, at this point, we only have to show now that you can find, for a given matrix R of this form lambdas, we want to show it can be written as V from J1, J2, that up to V inverse, where each Ji now just has the same lambda on the diagonal, and then once like that, right? So the proof was boiled down to this case. And we then further observed that this lambda plays no role in this game, so we might as well look at R minus lambda I, in which case all these blocks are 0 blocks, these are just zeros, and we just call this as Z's instead. Okay, so it has some Zn1, Zn2, like that. And like that. Right, so this is the nilpotent case. So the matrix R now is strictly upper triangular. Right, and that's what we did. Okay, so we looked at lots of examples, and we decided that the way we're going to compute this V is by finding Jordan chains. Right, so the columns of V form Jordan chains. In particular, if I look at, so let's just take again, it's best to talk in terms of examples so we don't get overwhelmed with notational details. So let's say that my R is such that I would have ended up with something like this. Let's say I would have ended up with Z3, Z2, Z5, maybe, like this, V inverse. Then we realized that if you look at the columns of V, we should block it into 3 blocks, V1, V2, and V3, where we put 3 blocks, columns here, 2 columns here, 5 columns here. Right? Same thing for V inverse. We have to look at its rows and block it off into, let's call them, for lack of a better word, let's call them W1H, W2H, and W3H, and then again it will be split in 3, 2, and 5. And the reason is that if you write out this as like in this form, so you can write this out again as 2 things, just to remind you, RV is equal to V times Z1, Z2, Z3, right? And if you write it the other way, it is W inverse, V inverse R is equal to Z1, Z2, Z3 times V inverse, right? You can look at it both ways. Then we realize that if you look at this block column by block column, we have something like this. V2 is equal to V2, Z2. Sorry, this is Z1, Z3, Z3, Z2, Z5. Z3, Z2, and Z5. Right, so the defining equations for these columns are in blocks. Okay, that's the key thing. And same thing for the rows of V inverse, they also appear in blocks. We have W1H R is equal to Z3 W1H, W2H R is equal to Z2 W2H, and then W3H R is equal to Z5 W3H. Okay, so you should make sure that these equations make sense to you. Right, they almost look like the right eigenvector equation and the left eigenvector equation, but except that these V's and W's are not columns and rows, they just block skinny matrices and fat matrices. All right. So in the proof, when we're trying to find this v, or the same thing, finding v inverse, what this tells you is that you have to think of v in terms of columns, in particular in terms of block columns, and we must think of the v inverse in terms of block rows. Okay. So this is the only complication over the other decompositions we did. In the other decompositions, LU, SPD, and QR, we could always do it column by column or row by row, and it was always a kind which one we should think about. Okay, here it has to be block columns and block rows, and this definition is kind of a mess, okay? But you see that within a definition it's in pairs. So V1 and W1 are linked together by the same Jordan block. Okay, so these two are linked, and V2 and W2 are linked by the same Jordan block, Z2 and so on. Okay, so you have to compute right eigenvectors and left eigenvectors sort of at the same time for the same block in some sense. Right, notice now that you can't use eigenvalues to distinguish these guys because these all correspond to the eigenvalue 0. Okay, so that adds to the complication. All right, so what did we notice about these Jordan blocks? So about these Jordan chains, so if we look at the first column of the first block column, for W1H, let's say we call them little W1H, little W2H, and little W3H. So these are the first 3 rows and columns. Then we know that R times V1 will be 0, R times V2 will be V1, and R times V3 will be V2. Okay, so this is just me writing out this expression explicitly. Right, we did that in the last class. Okay, what about for this one? For this one, we have W1H, W2H, W3H times R is equal to Z3, okay. So 0, 1, 0, 0, 0, 1, 0, 0, 0, and then you have W1H, W2H, and W3H, like that. Right, so if you look at the first two on both sides, we get W1HR is equal to W2H, and then we get W2HR is equal to W3H, and W3HR is equal to 0. Right, so we notice that these Jordan chains, so these V1, V2, V3 is called a right Jordan chain, and W1, W2, W3 is called a left Jordan chain, but the ordering is opposite of each other. If you look at this Jordan chain, for the right Jordan chain, V1, V2, V3, V1 is the eigenvector, because R times V1 is 0 times V1. The remaining just lead to each other, right? So if you start with V3, you can get, by just multiplying by R, you can get V2. From V2 multiplied by R, you can get V1, and that will be the eigenvector. Right, so V3 is the top of the eigenvector Jordan chain, but it starts on the right hand, and the eigenvector is on this side. For W is exactly the opposite. Okay, so W3 is the eigenvector, and W1 is the start of the Jordan chain. So if you take W1, apply R from the right, you get W2. From W, apply R from the right, you get W3, and then W3 is the left eigenvector because W3H times R is equal to 0 times W3H. And the 0 is the eigenvalue over here. Okay. All right. So these two things run opposite. And of course, these 3 columns and these 3 columns are related to each other. Why? Because they are part of V and V inverse. So we know from V times, so we know from this equation, V inverse V is equal to identity, that if you look at W, what do I call it? W1, H, V1 is equal to identity 2. Right? So this is a fat matrix times a skinny matrix equal to square identity matrix, right? So this is called a dual basis. It's not full of bases, but right. So the first row of W1 is perpendicular to the second and third columns of V1. The second row of W1 is perpendicular to the first and third column of V1, like that. Okay, so an orthogonality relationship holds. Right. So these are all the defining conditions, and when we construct V in the proof, we must satisfy all of these constraints, right? And the nice thing is that it's actually happens to be the converse also happens to be true. If you can construct any V and W that satisfy these conditions, we will end up with a Jordan decomposition. Okay, of course, that's just a guess, but that's what we're going to do. Okay, so these are the properties of the numbers that we must write down. We have to find these numbers for a given R. All right, so the proof itself is fairly trivial. Once you realize all this, it's just a matter of doing some long computation and checking everything comes out as you expect. Okay, so the proof is quite trivial. So we say that we first find the smallest value of k for which R power k is 0. Remember, this is a nilpotent matrix, right? Strictly upper triangular, so we know eventually the power will go to 0. we find the smallest integer k for which it is 0, and that k minus 1 is the largest one for which r power k minus 1 is not 0. Okay, so k is sometimes called the nilpotency degree. Right, so that plays a big role. Right, that essentially tells you what is the size of the largest Jordan block in this matrix. So the largest Jordan block in this decomposition will be k by k. That's what it says. Okay, so that's what it gets. So then what we say is that we can construct the Jordan chain now by this guess, which we went through last time. We know this is not 0, so you can always pick a w. I'm going to flip this, but I'll stick with the notation in the notes. So that this is not equal to 0. Okay, you can always find such a w. It's very easy to pick, so we just do that. Right, and then our right Jordan chain, which is our conjecture, will be, right, so we'll put a question mark, but will be r power k minus 1 w, r power k minus 2 w up to r w times w. And this will give us that v1 that we are looking for. Okay, that is our conjecture that this is the way to construct the right Jordan chain. Notice that almost no computation is required, but you do have to find the powers of R to make this happen. Okay, so it's not like doing Gauss elimination, but it is very tedious, and it can only be done, it has to be done exactly. So you can't do it in MATLAB, right? Because you need to find cases R power k is exactly 0, right? So all the cancellation will be perfect. Right? And floating point arithmetic does not guarantee that. All right, so this step is just usually done in our heads, or if there's some integer matrix or something, we can try to carry this out. All right, so that is our V1. And again, notice the motivation is right. The top of the Jordan chain should be on the right. The eigenvector should be on the left. And this is indeed an eigenvector because we write R times r power k minus 1 w, you get r power k w, which is equal to 0. Right, because r power k itself is 0. So you get 0 times w, right? So we know for a fact that this is indeed an eigenvector. What we don't know is why is this a Jordan chain? We don't know that, but that's our conjecture, that is going to be the Jordan chain. Notice it's just obtained by taking the Krylov sequence starting at a suitable point. If it's the longest non-trivial Krylov sequence you can construct for this matrix R. Right, that's where we start. Right, so now if this is going to be even has a chance of being true, remember this matrix, this is going to be the first part of the matrix V, so it must have linearly independent columns, otherwise matrix V cannot have an inverse. Right, so the first thing we should check is that V1 has linearly independent columns. Right, otherwise there's no chance of being part of the V we're trying to construct, which has to be invertible. All right, so how do you check this? Well, you will check this by taking V1 times Z, setting it to 0, right? You can put equality because we can always pick Z to be 0. And then we have to check if Z is equal to 0 is the only solution. If it is, then the column is linearly independent. All right, so how do we do this? Okay, again, this seems like a very hard thing to do when you first stare at it. Because you see that you actually cannot do Gauss elimination on this matrix easily. So the trick is not to try too much to do Gauss elimination in the usual way, but just see what matrix you can multiply by from the left, and you see that you can actually multiply this matrix by R, for example, from the left. But you see, if you multiply by R from the left, it doesn't actually simplify the equation too much. So the trick really is to multiply by R power k minus 1. Okay, we know this matrix is not 0, but it's probably not invertible either. Okay, so you have to be a little bit careful. Okay, this is sort of violation of the previous way. Whenever we looked at a linear equation, we were careful to apply only invertible transformations. In this particular case, we're cavalier because we only need to check if Z is equal to 0 is the only solution or not. So if we introduce additional solutions, we don't care. The proof, okay? So you'll see that it doesn't matter. Okay, so we multiply by R power k minus 1. Of course, you can multiply every column from the left by R power k minus 1, and you see that all of them will have powers bigger than or equal to k. For example, this one will become R power k times w, which is, since R power k is 0, the first k minus 1 columns will all be 0, and only this column will be non-zero. So when you're done, just get everything 0, get R power k minus 1 w, z, and we know this is non-zero, is equal to 0. That's the equation, right? But we know from this that if you look at the columns of z, now you'll have z1, z2, let's call it z. It's easier if you match it by the powers, zk minus 2. Z0 must be 0, right? I'm indexing it from the bottom to the top to make it easier to see the powers. then you see that this equation just says this component times this column has to be 0, and this column is not 0, so therefore this number has to be 0. It has no choice, right? So therefore we say that this guy has to be 0. We don't know about z1. All right, so that forces the last component of z to go to 0. So then we do the same trick now, but we multiply k minus 2 now. So if we multiply by r power k minus 2 instead, r power r squared w, rw, and w, and then z is equal to 0. You see all of these components will again go to 0, because they at least r power k or higher. But this component will be r power k minus 1w. So you'll get this column will be r power k minus 1w, and then you'll get r power k minus 2w times z is equal to 0. This is not 0, and this is not 0. Right, so the last two columns are not 0 now, but the last column doesn't matter because we already know that the last component of z is 0 from the previous proof calculation. So therefore, the only thing that matters is this number z1 times this has to be 0. We know this column is not 0. That forces z1 to be 0. Right? All right, so this is a very funny way of doing Gauss elimination on this matrix. But it can be done, right? And again, there's a mental block to realize you have to multiply by powers of r from the left. Okay, but once you get over that, so usually the rule is if you can multiply by something, multiply and check, okay? It might pan out. So here we try that, it works out. So we showed that z equal to 0 is the only solution, so keep going like this. We'll end up with z is equal to 0 is the only solution. That proves the columns of v are linearly independent. Okay, the columns of v are linearly independent. Most of the proofs that are incorrect about Jordan decomposition fail to check this step. Okay, so you should be careful, okay? You have to check the step. And that's why we have to start from the top of the Jordan chain, not from the bottom. All right, so now we have columns of V1 linearly independent. So we have to construct the corresponding left Jordan chain now. Okay, so to construct the left Jordan chain, what I'm going to do is going to start with this. I'm going to, okay, so I have this matrix V1, right? And this is a skinny matrix, k columns in it, and it's got full column rank because it's linearly independent. All right, so now I claim. So remember, the first column, first row of the left of the inverse of V must satisfy this equation, right? So it must be that if I find a row, the first row of V inverse must satisfy this equation 1, 0, 0, 0, right? That is the first row. V inverse times V, the first row will satisfy this equation, right? So we can say, well, why don't we? And we know that would be the start of the Jordan chain for the left Jordan chain, right? It has the first row of W is the start of the Jordan chain, and the bottom is where the eigenvector lies. So it makes sense that why don't we just try to find such a row vector, right? Problem, of course, is highly non-unique, right? Because if you look at this equation, it is just v1 times y is equal to e1. So, sorry, v1h. And v1h, of course, is a fat matrix with full row rank. So it's got many, many, many solutions in general, right? We don't care because this is a fat matrix with full row rank. There's at least one solution. We just take some arbitrary one. Okay, we don't care which one we pick. It always has a solution. We just pick one. Okay, we call that guy y. So you see that the left Jordan chain is highly non-unique even after you fix your right Jordan chain. Okay, there are many, many, many choices of this, which is kind of weird, but it is there. So we just pick some y. Okay, so once you pick y, then of course, you know, you naturally you want to form the left Jordan chain. So the left Jordan chain will be yh. So you form fix wh. Let's call it wh. So if this will be yh like this, then yh r then you go yh r squared, right? So you just form the length k Jordan chain. And my guess is that this is going to be the correct left Jordan chain to use. Okay, so to be 100% sure, we must check that the other equations are true, right? And there are lots of checks to be done. So let's just list some. For example, we checked here the columns of V1 are linearly independent, but we never actually checked if it's a Jordan chain or not. So we should just do that, and that's easy to check. So we just observed that the equation satisfied by V1 we wrote down earlier was this one, right? R times V1 should be equal to V1 times Z3 in that case. So here in our case it should be ZK. We should check this, but this is trivial to check, right? If you multiply V1 from the left by R, you see that everybody moves over to the right by one unit, one column. But that's exactly what this means. V1 times ZK means they shift all the columns to the right by one. All right, so that's the trivial check, so I'll leave that to you. Okay, so what we did construct is actually a Jordan chain. It behaves the right way that the equations want. Okay, similarly, you can check that these are actually a left Jordan chain too, the way we constructed it. So you can show WH times R will be WH times VK. Okay, so it will all shift up as expected. Okay, so it is a Jordan chain. However, what we don't know is whether the columns of WH are linearly, the rows of WH, are they linearly independent? They have to be because they'll be part of the inverse of a matrix. Are they linearly independent? And actually, are they the correct duality conditions with V1? So remember, we want to make sure that WH V1 is the identity matrix, right? Because these are the rows of the corresponding columns in the inverse. So they must be satisfied the relationship, otherwise they cannot be true. So this has to, we have to check whether this is true or not. Right? And this is where this condition comes in. So this is where this condition comes in. This thing comes in over here. Okay, again, I'm going to leave you to check. If you open this up, you'll see you have Y sitting right there. And then V1 sitting right here. And then you have YH R like that. You know for a fact, you picked YH V1 to be 1, 0, 0, 0. Okay, so the first row is definitely true. You just need to check the other rows are true or not, but that's a trivial calculation. Okay, so you just multiply it out, check it out, it'll come out to be true. Okay, so the way we constructed the left Jordan chain and the way we constructed the right Jordan chain happened to just somehow neatly, but just by luck, satisfy all the equations we want without any further trouble. Okay, so and by the same argument that we use for V, you can prove that the rows of W are linearly independent. Okay, just a repetition of the argument that I did over here for the columns of V. So you can show the rows of WH are also linearly independent. Or you can just see it from here. If the rows were not linearly independent, then this could not be true. Right? Because then you can have, this will have a left null space and identity has no left null space. So like everything you learned before will appear in 1 second and disappear. Okay, so everything that you knew about Gauss elimination, left null space, right null space, fat matrices, skinny matrices, will be used very rapidly in this proof. So it's essential that you go back and look at this old stuff, make sure that you understand this stuff, and it's sort of, it's at your fingertips. So you can do these long calculations without too much of tedium. All right, so we've done these two. So we have a left Jordan chain, we have a right Jordan chain. We're almost at the end of the proof. Okay, the rest of the proof is actually quite trivial. But sometimes when proofs get very trivial, it's also very hard to find them. The human mind just doesn't like too many choices sometimes. And now we're just down to the easy part. Okay, so the easy part is what I would call a very trivial calculation. So these are called matrix completion problems. Okay, so what we've done now is that, okay, so we've constructed a matrix V where we know what the first 3 or k columns are, but we don't know what the rest of it is. Okay, so we need to find the similarity transformation that is going to make into the Jordan form. For one Jordan block, we found the columns of the right Jordan chain. So we know the first k column, but we don't know the n minus k columns here. We know what, right? But what we've done is we've also constructed V inverse, where the first block row is W1H, or WH I call it, I think. What do I call it? WH? But we don't know what the remaining minus k rows are. Okay, so I know something about V, I know something about V inverse. Okay, I know that these are not incompatible, because I'm guaranteeing that WHV1 is actually identity. Okay, so I do satisfy partially what it requires to be inverse. What I need to show now is that I can throw in some numbers over here and some numbers over here, such that this is actually V inverse and that's actually V. Okay, so if I multiply these two matrices after throwing in these remaining numbers, if I multiply this with that, I should get identity. Okay, so these are called matrix completion problems, and they arise very, very often in engineering. Okay, very common in inverse problems and stuff. You make some measurements, for example, because you have to only measure things on the boundary of a system, and you want to know what's on the inside, and then you'll end up with a matrix completion problem. Okay, so in any controls problem, this is also very common. So this is a very heavily studied problem, but in this particular case, it's actually quite trivial. Okay, this problem, even though it looks funny and looks nonlinear, is actually quite trivial to write down the solution. We'll just outline a process. Okay, so you can actually do this just by Gauss elimination. Even though the problem looks weirdly nonlinear, it is not. Okay, so let's write it down. Okay, so the trick is the same trick that we used before in the XY transpose kind of problems that we had. Okay, first thing we observe is that I want to embed the columns of V1 into an invertible matrix. So let me just guess one by just brute force. Okay, so first I try to find a matrix G inverse such that G inverse V1 is identity 0. Okay, why is this the same as embedding the columns of V1 into an invertible matrix? And that's trivial, right? Because if I take G to the other side, then this is saying G times identity 0 is V1, which is the same thing as saying as G as V1 as the first few columns, right? That's exactly what that thing is saying. All right. But this is trivial to do, right? You already did that in the homework. For example, you can do LE factorization of V1 and then throw out the 0 part of U and put something in there and things like that. Okay, you can finagle something out of it. So this is trivial to do. Okay, make sure that you can do this. Right? You can use QR factorization. You can do all kinds of stuff to do this, right? Because V1 is full column rank. All right. So you can find some matrix where the first few columns are exactly V1. The rest are filled up in such a way that the matrix is invertible by construction itself. All right, G is a square matrix. Otherwise, I couldn't write G inverse. All right, is this clear? All right, so if you look at G, it's got V1 sitting in the front and some stuff sitting at the back. And so square matrix is invertible. Right, so we partially have thrown in the numbers over here. Okay, so now we must fill in these numbers to be compatible with that stuff that we threw in over there and still get an inverse correctly. Okay, so how do we do that? Okay, so we know some relationship between the rows of W1H and the columns of V1, right? So that is our guiding constraint now. So we know that we satisfy this equation already, right? We verified that. We satisfy this condition already, right? So now we just fiddle with the stuff in between, okay? So we say, well, okay, I don't have V1 anymore. I have G and G inverse, right? I want to work with this guy. So what does this tell me, right? I'm hoping G is the answer, of course, but I have to check if G is the answer. So if I look inside this, G inverse V1 was chosen to be identity 0, right? But what about WHG? Well, who knows, right? I mean, we could pick any G that does this job. Not all of them are going to satisfy the constraints that we have. So we've got to look inside it. All we know that this is a fat matrix times a square matrix. We're going to end up with a fat matrix. Let's call it W11 and W12H, like that, right? We don't know what these numbers are going to be because we had barely any control on G, other than that it's invertible, and the first few columns that we want, we had no control over it. Okay, so that's the best we can do as identity, right? So if you multiply this out, we get W11H, identity is equal to identity, from which we realize that this isn't the identity matrix. So this is definitely identity, but there's nothing you can say about that guy over there. All right, so there's some residual stuff left over, which is not good. Why? Because you see that we want the first few columns of G to be WH, and that is no longer true. So we want WH to be identity 0. Why? Because we want WH to be the first few columns of G inverse, right? That's what we want. This is what we would like to have. Right? That's the requirement, that we should complete the matrix such that V1 is the first few columns of V and WH is the first few rows of V inverse. Right? And our candidate for this is G, and the first few columns of G are definitely V1, but we wanted this to be true, right? WHG to be identity 0, but we get some crud over there that is not. So we've got to get rid of this. So we modify G a little bit now. Okay, the way we're going to modify G a little bit is by saying that, well, okay, I'm going to insert a Gauss elimination transform inside between those two guys. I'm going to say, well, okay, let's look at WHG, and I'm going to insert a Gauss transform. And you see that you need to eliminate towards the right on the columns. So we can think of the Gauss transform as being I minus xi, and then I xi, and then we have G inverse V1 is equal to identity. Right? So this time that is clearly the identity matrix. So that's my Gauss transform. Right? Over here I have identity. Right? So I need to multiply. So I'm modifying my G with this extra square invertible matrix. G times this. And G inverse times that is going to be G inverse. Right? Okay. So that's going to be the correct V that I'm after. Right? So we want this times this whole at the very end. So I want this to come out to be identity 0, right? But that is easy to do. You see, I just have to pick x, b, b. You just Gauss elimination, okay? So written this funny way. So you plug it in over here, plug it in over here, and check that you don't screw up this side now, okay? So if you multiply all this, you definitely get identity 0. Here, what do you get, right? Here you get identity W1, 2H, identity times identity 0, and that is still identity 0. Okay, so everything is fine, right? So this is that part. This is that. All right, so we're done. So now we know what a V matrix is. We should just take V to be identity W1, 2H, identity G inverse. This is invertible, this is Cayley invertible, this is a Gauss transform, so we're done. Right, and we've made sure that the first few columns of this V matrix are V1, and the first few rows of V inverse are W1H by construction. If not, you should go back and find everything out and make sure that I didn't mess it up. All right, and now it's trivial, okay? So now if you just apply this G, so the rest of the calculation is fairly, so that's V inverse. If you look at R inverse, G inverse G, you'll actually get ZK, 0, 0, and some stuff over here. All right, and again, you should verify this, and then the rest of the proof is by induction. So now you have a smaller matrix to worry about. Go away and do the proof again one more time on that guy until you're done. All right, so this is the left-right proof of the Jordan decomposition. Like I said, in Colmeyer's book, this is not how it goes. And actually, I've never seen any book that has this proof. The traditional proof is just to keep going this way. Construct another Jordan chain that's linearly independent of the previous Jordan chain. Okay, so that is the part that is difficult. And again, most engineering textbooks get the second part also wrong. Okay, they first mess up in how they construct the first Jordan chain, but they also mess up when they construct the second Jordan chain. Okay, again, you have to be very careful. You have to make sure that the second Jordan chain is linearly independent of the first Jordan chain. So you need to prove that. Okay, and also many abstract proofs get this part also wrong. Okay, if you don't prove it and just say, oh, there exists a Jordan chain, that's useless. Maybe you end up with the same V1 over there too. Right? I mean, in case clearly the matrix is not invertible after that. Okay.
There is a V inverse on the VK00 star or T?
What was, oh, the other way maybe?
Here was T.
Oh, sorry. This will be, yes. My mixed notation there, sorry. Okay, that's a good point. All right. So this is the Jordan decomposition, okay? I really don't think there's nothing to be gained by reading this proof or reading anybody else's proof of the Jordan decomposition. As far as I know, most people don't read anybody's proof of Jordan decomposition. What you should do is think of this as a very long, extended exercise that you should really do by yourself. Okay, just try to come up with your own proof. Really, there's no point reading somebody else's proof of this. It's just the calculation is too long, and you don't learn anything from it this way. Okay, but all I wanted to show you is that when you do this proof, you can appeal to things that you've learned before, and you can use them to construct a proof. Okay, so go away and try to do it by yourself. Okay, so if you want to be comfortable with Jordan decomposition, you should be able to do the proof yourself. Okay, because in real life, you are probably to make some modifications with this to get decomposition that works for your problem, right? But this decomposition is catering towards a power of n, right? Which is not all problems in the world. So, all right, okay, so we're done with Jordan decomposition, and now we go back to where we started from. Okay, so we can construct the Jordan decomposition with pen and paper, not in MATLAB. Okay, and don't use anybody else's code that computes Jordan decomposition either. Right, it's just a theoretical construct. Question?
Does MATLAB use symbolic computation to do Jordan decomposition?
It can. Yeah, you can do symbolic computation, but symbolic computation is extremely slow, so yeah.
But if you do like a 6x6 matrix?
You probably will succeed with 6x6. I think you'll start straining memory if you go to 10x10 probably. There are also codes that are called what are called multi-precision codes. No, they're called arbitrary precision codes. These are codes that will allocate more and more bits to the floating point numbers as you proceed. And sometimes the strategy works out reasonably well. But the problem, of course, is division, right? I mean, as long as you do multiplication, if you multiply two numbers which have 10 bits each, you have at most 20 bits. So you can manage this strategy. But of course, if you divide two numbers and you want to rewrite them as a single real number, then of course, you cannot do it in general. So you run out of bits that way. So you could try to keep a rational form of multiprecision and get away with it too. That's also possible sometimes. But these codes are extremely slow. Like say, for example, like you say you want to do a calculation in double precision, right? So that's native to the machine, it's extremely fast. Most modern machines, other than a GPU, will do roughly one double precision operation per clock cycle, maybe a little bit more if you're vectorizing and using the internal vector units. Okay, so it's very, very fast. In particular, Intel x86 machines don't actually go any faster for single precision versus double precision. The only speed difference is, you're using the memory bandwidth much more efficiently for single precision versus double precision. But once it's in the cache, then that cost difference goes away. However, if you try to emulate, say, quadruple precision, right? If you have any Linux, just install this 4-times package libquad. It emulates twice as many bits, so you get about roughly maybe 32 bits, 32 decimal digits maybe, using just 2 floating point numbers. Right? So oh, this should be extremely efficient, right? It doesn't allocate any more while it's running. It just doubles every quad precision number stored as 2 floating point numbers, floating point numbers. So just twice as much. It cannot be that much worse. But if you time routines in double precision and time routines in libquad, it's about a factor of 100 difference. Even simple things like multiplication would be 100 times slower, even though you expect only like a factor of 2 or 4. Of course, part of the reason is because you're just stressing out the memory bandwidth. The memory, the access from main memory to the CPU much more when you double, right? Remember, on modern machines, your bus is running roughly 10 to 100 times slower than your CPU. So most of the time, even though you might have a 4 gigahertz processor, your memory is what is deciding the time that you're spending. Right? That's why LA-Pack now written in a very clever way to first bring all this stuff into the cache, then do all the operations, then bring more stuff into the cache, stuff like that. Okay, so that's why it's not easy even to write matrix multiplication. If you don't do it well, it'll run about 10 times slower than, say, GoToBlast. Okay, GoToBlast is the name of a person. Okay, so that's what most people use these days. Okay, now, so in general, you cannot do Jordan decomposition for anything of engineering interest, but still, it improves, of course, it arises all the time. So you have to be careful about that. Okay, so now we're going to use the Jordan decomposition to do something useful. So remember that when we started it off, our goal was to compute a power of n. If you look at a particular solution for 2 right-going solutions, say your system will say u of n is equal to u of n plus, n plus 1, u of n plus f of n, then we know that if f is right-going, the particular solution would be a to the power of n step function of n convolved with f. Okay, this is horrible notation, right? So forgive me, but that's the electronic notation. So, of course, if you write this all out, it'll just be a sum a power minus k, f of k like that. Right? So, or if you want to write, yeah, we can write it like this, that's fine. Right? It's a combination of those 2 sequences. So you see that what we have to evaluate is in general some polynomial function of a, basically. Okay, so what we really care about, right, if you look at this component by component, is a polynomial in A. So we want to evaluate polynomials in A in general. So we generally need to be able to evaluate expressions of this form. Now, in general, in practice, see, I noticed I dropped both the lower bound and upper bound in the sum. In general, in practice, you might end up with, all powers of A being used. Then, and we would call that a Laurent series in that case. You might go from, minus 3 to 10. You can get all kinds of funny things like that. I would refer to all of them as polynomials, okay? To an engineer, after a while, the infinite sum is a headache if it doesn't converge properly. Okay, but if it's not converging properly anyway, you're in trouble way before you reach this point, okay? So you should go back and look at where you got into trouble in the first place. Right? In physics, it's a different story because for them, almost none of their sums converge anyway. So, but for engineering, it should all converge. There should be very rarely any reason to put your thumb into something where it's not converging. So I won't be very concerned about this kind of issues over here. Right? I would call all of these as polynomials. All right. So we need to evaluate things like this. And the goal, of course, was that the Jordan decomposition makes evaluation of these things very nice. Okay, it should be very easy to evaluate this. There are certain calculations that you can just do with a short decomposition. Okay? You don't need to do every polynomial with the Jordan decomposition. For example, the Cayley-Hamilton theorem. Let's talk about Cayley-Hamilton. I don't know why people think that this is very important in practice. And most of the time when I see engineers using the Cayley-Hamilton theorem, it's all for the wrong reasons. Okay, you should never need as an engineer to use Cayley-Hamilton. Okay, Cayley-Hamilton is useful in algebra, but very rarely in real floating point arithmetic or anything that engineers, you and I would do. But anyway, people think this is important. So I'll tell you what Cayley-Hamilton is. So remember when we started the proof, we looked at this sequence I, a squared, a cubed like that, a power n squared, the sequence where A is an n by n matrix. We said this is a Krylov sequence. And we said that this is a n squared plus 1 vectors in an R n squared dimensional space, right? These are all column vectors in the space R n cross n, if A is an n by n matrix. Okay. And our proof of the existence of the eigenvalue was based on the fact that there's a linear combination of these columns that must go to 0 because there are n squared plus 1 vectors in an n squared dimensional space. They have to be linearly dependent, right? That's what we depended upon. So naturally the question arises, what is the actual dimensionality of the space? Right? If you look at the span of this set, if you look at the span of the set, what is it? Is a vector space, subspace of R n cross n, but what is the actual dimensionality of it? It turns out it's nowhere close to n squared. Okay, it turns out the dimensionality of the span, so it turns out the dimensionality of this n size of the matrix. Okay, so that proof is actually a little bit tricky, but a variant of this is called the Cayley-Hamilton theorem. Okay, so the Cayley-Hamilton theorem, but most people say the Cayley-Hamilton theorem in a slightly different way, because I'm going to state it now. So let's say that we take A, and I'm going to state it with a Schur decomposition, and we find a Schur decomposition of A, right, which only uses unitary transformations. And if we look at the diagonal of R, then there are some numbers sitting, lambda 1, lambda 2 up to lambda n. This time I just label the numbers as they arise from the diagonal. They might be equal to each other for all we know. Okay, then from this, notice there are only n numbers over here, right? From this we can form this polynomial which is called the characteristic polynomial, which is just x minus lambda 1, x minus lambda 2, x minus lambda n, right? And this, notice that the degree of this polynomial is exactly n, right? Normally you will define this polynomial by going through determinants and talking about determinant of a minus lambda I or a minus xi in this case. Okay, here since I did not introduce determinants, I just avoid that guy. Right, so this is called the characteristic polynomial of this matrix. Okay, and it's just defined through the Schur decomposition in this case. Okay, this polynomial is well defined as unique because by now we have shown that these lambdas are unique, so we are done with that part. Okay, so this is a well defined polynomial, right? And the Cayley-Hamilton theorem just says that P of A is 0. If you take the characteristic polynomial and stick the matrix back inside it, you will get 0, which then proves this theorem too. Okay, I'll leave you to figure that part out, but all right, so that proves the span condition. So make sure that you understand why, if this is true, then this must be true too, right? But more importantly, I want you to go away and prove the Cayley-Hamilton theorem with just a Schur decomposition. So you don't need Jordan decomposition for that. You just take this thing, take this expansion, stick it into this polynomial, evaluate it, and show you'll get zeros. Okay, so you should all go away and do that. I mean, you can prove the Cayley-Hamilton theorem. Okay, I've actually had one guy tell me that if you don't know linear algebra, you can prove Cayley-Hamilton. So I feel obliged to tell you what Cayley-Hamilton was. Okay, but I've never actually used it in my life. So it's there. Okay, so that's Cayley-Hamilton. Okay, so you see that polynomial. So coming back over here, though, so definitely in discrete systems, you need to evaluate this polynomial. Some polynomial, okay, come from the convolution, whatever. You need to evaluate this polynomial. You need to understand how the polynomial, the graph of the polynomial, if you look at P of x, how the graph of this polynomial is related to the entries inside this matrix. Right? That's what we care about as engineers, right? What are the numbers in the matrix? Because that's the numbers in my solution. Right? We need to understand how to go from here to here and then back and forth. Right? In the design problem, we probably go backwards, but still, you have to understand this relationship. Right? And then this thing is, because it's common, right? All of physics, all of engineering is concerned with dynamical systems, and we have to talk about this. It's just ubiquitous, right? And there are many, many, many variants of this problem. For example, if I look at differential equations, then the infinite degree polynomial is this function exponential of x, right? Which is defined as 1 plus x squared over 2 factorial like that, right? Which is infinite degree polynomial. Right? Notice that this is a bad habit to call this function e power of x. Huh? This is a bad habit. Okay, you should eventually avoid that habit because e power of x. You know, when you take the root of something, it is not a single-valued function. It's a multi-valued function, right? Of course, conventionally, when we take e to the power of x, we pick a certain branch of the logarithm, so it's sort of we don't worry about it. But in real calculation, this will eventually lead you into trouble, okay? Especially in this class. If you write like this, you'll confuse yourself. All right, you'll see as we go through, okay? You'll be a little bit careful. Same thing with log and square root and cube root and stuff, right? Those are not single valued functions. They're multiple valued functions. So before you use them, you sort of have to make up your mind which root you're talking about, which cube root you're talking about, and so on and so forth, okay? So you'll be a little bit careful about this. So it of course applies to e power of x too, all right? Okay, so we'll try not to write that myself, though sometimes laziness will take over and write it down. Okay, that's exponential of x, right? So obviously e power of exponential of the matrix A t arises in the solution of differential equations, right? So that's again something like this, and you would like to know how the entries of this matrix are related to the entries of matrix A. Right, we would like to do that. And then of course, if you look at second order differential equation systems of second order differential equations, so, you have columns, you have d by dt squared of u of a times d by dt of u of t plus b times u of t is equal to f of t, like that. You have second order system of differential equations. Of course, you can rewrite them as first order systems if you wanted to by stacking u and u prime together into one long column. Yeah, that would be the state space approach. But sometimes it helps if there are symmetries in the matrix A and B to stay here and solve it this way too. Okay, in that case, if you do it, you'll see that what will arise is that the impulse response will depend upon this matrix and this matrix. Okay, this will arise naturally in that setting. If you want to know more about it, just look at Strang's book. He does the second order case too. I don't do the second order case. It's not difficult to work it out yourself. Okay. Right, again, the expression is what you expect, right? So remember, sine of x is defined in mathematics like this, like that, right? That's the definition, and cos of x is defined the other way, like that, right? So those are the definitions. Okay, just make sure that you don't have two definitions of sine and cosine in your head, because then you'll get into troubles. All right, right? So you define them in terms of numbers. These are good enough. All right, so those are definitions. You also, because you can get exponential of a matrix, you also get log of a matrix. You also get square root of a matrix. You can get matrix with some weird powers and stuff like that. All right, all of these will appear in real life. Okay, and of course, in every case, we want to understand how the numbers that go into the function affect the numbers that come out of the function. Right? Just like normally for single input, single output functions, we just look at the graph of the function. That helps us understand how the number going in affects the number coming out. Right? But when you have multiple numbers going in and multiple numbers coming out, of course, it's not easy to graph these things. So you need to have some other way to understand how the numbers going in affect the numbers coming out. If I put in small numbers, we'll get small numbers out. You want to understand this, get a grasp of these things. Okay, so the Jordan decomposition comes in. Okay. So Jordan decomposition is nice because if I give you any polynomial, infinite or not, okay, so ignoring questions about convergence, we have P of A summation alpha n a power of n. So if you substitute the Jordan decomposition inside, then providing everything is converging nicely, which we'll talk about in a second, then you just have to evaluate this, which is the same thing as V times P of J times V inverse. Okay, so what the Jordan decomposition says is that to understand how the function affects the numbers in the matrix case, you don't look at the whole matrix, you just need to know the Jordan form, which of course has lots of zeros in it. So hopefully the connection to the input and the output is shorter in our heads. Okay, so and it turns out you can actually do much better than this. All right, so we're going to look at this now and see how it's actually used. Now, this part, I'm going to cheat a little bit. We're talking about polynomials and infinite degree polynomials and so on. And of course, the natural place to do this is inside complex analysis, right? The study of power series. Notice that all expressions are all power series in X. They are arbitrary sums, but power series. And of course, the study of power series is called complex analysis. And you all should take a class in complex analysis. 30 years ago, it was a natural part of your calculus sequence. Every engineer would take complex analysis in their sophomore year. Okay, but now, for some reason, almost no engineers study complex analysis, but they all study Laplace transform, which is kind of bizarre because you can't understand Laplace transform if you don't know complex analysis. You study Fourier transform without knowing complex analysis, which also cannot be done. Okay, so you should all take a class in complex analysis or read a book. Okay, there are lots of good books because this subject has been taught engineers for hundreds of years now. So the old book that I use as an undergrad is still good. So Churchill and Brown has the advantage of being short and sweet. I have a brief 3-page or 4-page introduction to complex analysis in my class notes. You can just work out the problems yourself if you're brave enough. If you remember your multivariable calculus, it's fairly trivial to do it. It's not a hard subject at all, okay? Complex analysis is actually quite easy subject. I would say it requires about a week to 2 weeks to sort of get enough of it under your belt. So you should take it, okay? Unfortunately, at UCSB, I think the undergraduate sequence is 3/4 long, which is unnecessarily long. But, a week or 2 weeks of your time, you should be able to get it done. But you should read it, okay, and understand how complex analysis actually works. All right. But so in my notes, I do functions of matrices in the right way, but in this class, I won't do it that way. Okay, so people who want the right complex analysis approach should look at the notes. People who want just a quick and dirty version, I'll just do it in the lectures over here. All right, so how do we evaluate a polynomial of a Jordan form, right? Remember, the Jordan form is made up of smaller Jordan blocks like that, right? Again, it's easy to check if you have a block diagonal matrix like that, then the nth power is j1 part of n, 0, 0, j2 part of n, like this symbol. It's easy to check, multiply it together n times. It's a block diagonal matrix, so it should behave like scalar diagonal matrices. Therefore, from this, we can easily establish now that we just need to apply the polynomial to each Jordan block one by one. It's called K, like that, right? So when we're computing functions of matrices, it's enough to be able to apply that function to one Jordan block at a time, one of the elementary Jordan blocks. And an elementary Jordan block just looks like this, okay? It's got lambdas on the diagonal and ones on the off diagonal. So we only need to understand how any function behaves on this single Jordan block. Once we do that, in principle, it's just elbow grease after that to figure out how the whole matrix is affected. Okay, so we will only concentrate on a single Jordan block because of that. Okay, the rest of it is just notation after that. Okay, so you can fill in the gaps easily. So we'll just concentrate on this. So usually when you work on Jordan blocks, it's nicer to split this up into the sum of two matrices. Okay, you'll see why this technique is useful. It's better to write this as lambda I plus z. Okay, so let's say that this is a p by p matrix. Then this block is usually called J lambda. So this says what the size of the Jordan block is, and this is what is the number on the diagonal, right? And computation is lambda I plus zp there, right? And the reason for writing this like this is, of course, because these two matrices commute with each other. Okay, they form a commuting pair. That's what is critical. Okay, actually, almost nothing else is used, so this is the part that matters. So lambda I times zp is equal to zp times lambda I. So in calculation involving this matrix, these two matrices behave like scalar numbers, okay? Because they commute with each other. Then the thing that makes matrix algebra different from complex numbers or real numbers is the fact that matrices don't commute. But in this case, we will see that because this is the only thing that shows up and they commute with each other, whatever we do in complex analysis just carries over to these matrices. Okay, it will be really, really simple to calculate with these guys. The one thing that you have to be careful about, though, is that the powers of this are actually much better behaved than complex numbers. Okay, so Vp to the power p is equal to 0. So that's very important. Okay, which means that when you take powers of this, eventually it will become 0 and go away. So you won't get an infinite sum out of it. Okay, those are the two things that we will use. All right, so the rest of it is just elbow grease now, so we can compute. So we will compute that. Okay, so let's apply. So remember, we want to evaluate the polynomial of this guy, but the simplest polynomial is, of course, just the nth power. So we want to compute p of x equal to x power of n. Right? We start with this one first. If we can do this, then the rest of it should be a little bit more simpler to do. So let's start with this, see whether we can compute this expression for a Jordan block. That's what we started with anyway, so we should just do it first. Okay, so let's look at it. So if I apply this p to a Jordan block of size p by p, then this is what I have to compute. Right? I just have to multiply the Jordan block with itself n times. That's all I have, right? All I want to know is what do the numbers in the Jordan block look like, how are they related to lambda, and how are they related to p. Those are the two things that we, and of course, how they're related to n, which is the power that you're taking. So let's look at it. right? So the way to do this calculation, it's good to write this as lambda I plus Zp to the power of n. All right. So now comes our old bugaboo. We have to find an expression for this. But we've done this before, so it is right. So this is the multinomial theorem. So we'll just write it out. So remember when you worked in high school, if you write a plus b to the power of n, right, which is a plus b times a plus b times a plus b, then to get an expression for this, you just observe that you must form all possible products taking one number from each parenthesis at a time and then add them all up, right? That's how the product is formed. So for example, I can take the first number from everybody and I will get a power of n, right? And there's no other way you can get a power of n, right? Because I've exhausted that choice. You can also pick the second number from everybody and you'll get b power of n, and there's no other way to get b power of n, right? You can also make another choice. You can say from the first person at first parents I pick an a, from everybody else I pick a b power n minus 1, right? But I can also have picked the a from the second one and the third one and fourth one, so I can get this n times. So the coefficient in front of it will be n like that, right? So this is how that sum is. You should really make sure you look at this yourself and derive this result for yourself. Okay, so you see that actually, even though it looks like a mess, there's a fairly simple way to write down this power. We can write it like this. When you multiply all this, you'll always get terms of the form ak b power n minus k, right? And you have to pick a k times from n parentheses, right? And there are n choose k ways of picking them. So that must be n choose k times this term will be formed when you multiply, right? And all such powers from k equal to 0 to n will be used up. So that's the multinomial theorem, right? Either you wing it like the way I did it, or you prove this formally by induction. Okay, either way is fine. Right? So assume it's true for n is equal to 1 or n equal to 2, then you prove it for, if it's true for n, prove for n plus 1 like that. You can do it that way too. Okay, so this is the multinomial theorem. Notice that in this theorem, the only thing that we needed was that a and b commute with each other, right? Say for example, I pick a from the first term, and then I pick b, 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 then the term I get is like that. If I pick b from the first term, then a from the second term, and then I go b, 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 it's like this. But since the number of a's and b's are the same in both, and because a and b commute, I can write this as 2 times a, b, 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 like that. That's what I did, right? That's the calculation that we were doing. We only use the fact that the a's and the b's commute. We never use anything else in this expression. All right. So therefore, it follows that this expression must also hold true for this matrix power, right? Because these two guys commute with each other, and therefore they should hold. Okay, sometimes people will say this is a symbol calculus, okay? But I think that is more confusing than just saying, obviously I could just repeat this entire calculation like that and derive the proof one more time with a being lambda I and b being Zp, right? And then I will get the same result. So this is just sum over k is equal to 0 to n, lambda power n minus n choose k, lambda power n minus k, Zp power k. Okay, so now we have this expression written out. We can write it out in more explicit form to see what it looks like. Okay, so let's write it out. Okay, so this guy goes away. Let's write it all out now. So if I write all this out now, over here, right? So the first term will be lambda power of n, Zp power 0, right? Which is identity for us always, right? And n choose 0 is just 1. Okay, so there's one way to make no choice. Then the next term will be lambda power n, be n choose 1, lambda power n minus 1 Zp, right? Will be the next one. K is equal to 1, and then I'll get n choose 2, lambda power n minus 2 Zp squared, like that. Okay, so I won't write the right term, the last term, because you see that it depends upon the relationship between p and n. If n is bigger than p, then this series will terminate as Zp to the power p minus 1. If n is smaller than p, it will terminate as Zp power n instead. Okay, because Zp power p is eventually 0, so we will not stress out about this. Rather, we'll write it out like this instead. So you notice that if I write this out explicitly, it's very easy to understand. So this is just identity matrix, so this number sits on the diagonal. like that, which is nice, right? Because when you take the nth power of a matrix, which is upper triangular, we know that the diagonal integers we take the nth power of it, and that continues to be true. So we didn't at least mess up the first term. What about the second term? Notice that ZP is 1 in the first super diagonal and nowhere else. Therefore, this number will sit in the first super diagonal like that. Like that, okay? So lambda power of n, then you get n choose 1, lambda power n minus 1, lambda power of n, like that. All right? Then if you look at the next term, ZP2 has only 1 on the second super diagonal and nowhere else. Right? Therefore, this number over here, which is multiplying it, will sit only in the second super diagonal. And choose 2, lambda power n minus 2. Like that. Right? And you terminate either when this number becomes 0, or if you otherwise just keep going until you fill in the last block. Is it okay? Right, so that's the expression for ZP power of n. And you see that it's already a mess. Right? First of all, notice that if you ask what is the largest number in this matrix, it is a pain in the neck. Right? So now we see that transient phenomenon that I was talking about. Right? If lambda is smaller than 1 in magnitude, then the numbers are decaying from there to here, right? So because you have lambda power 1 somewhere there, and then it's getting smaller and smaller as you come towards the diagonal. Right? In other words, the matrix is fat away from the diagonal. To an electric engineer, there's always a cause for trouble because such matrices tend to have very large condition numbers, sort of like the antithesis of the identity matrix. So the identity matrix, if you look at it, it starts at 0 and then comes up to 1 and then goes back to 0 again, right? So all its weight is on the main diagonal, and its condition number is exactly 1. So it's a very nice matrix. These matrices are just the opposite of that. All the bulk sits up there and then they decay towards the origin. So the condition number would be very, very large. Okay, that's first thing. Second thing is you can still ask what is the largest number in this matrix. And notice that it is not clear where the largest number is, because even though the lambda is decaying as you come to the identity, the n choose k is like a Gaussian function. It goes up and then comes back down. So while the lambdas are decaying as you come towards the main diagonal, the n choose k is sort of going up and then coming down, and this product is what matters. So the largest number could occur somewhere in between, over here, right? And n choose k can grow extremely rapidly. Okay, so it's not something that you can say, oh, no, lambda is an exponential function, I can just ignore n choose k. No, n choose k can dominate for a long time before it decides to disappear. All right, so you have to be a little bit careful, okay? So even this, at this stage, we can see that we're in all kinds of trouble if we just look at the size of the numbers, right? And the size of the numbers is important in engineering. If something is large, it means we use a lot of energy, peak currents might be very large, the peak voltages somewhere might be very large, right? If I'm doing computations, I may have to use a large number of bits to hold some numbers, right? And if I don't hold that many bits, then I'll produce garbage after a while in the calculation. So for everybody, whether you're a programmer or whether you're an electrical engineer or a mechanical engineer, these large numbers usually spell trouble. Okay, so you always are sensitive to the occurrence in your calculations. All right, so we can compute a power of n now. Or we say something about its numbers. Okay, nothing as nice as we would have liked, right? So if I ask you what is norm of JP lambda power of n, it's still a tough question. Okay, I didn't answer that question, but at least you can compute the Frobenius number of this, for example, right? Which is never used in practice, but it can be done. All right. Right, so this is an important question. Okay, I'm not going to say anything more about it, other than the fact that it just seems like a pain in the neck even after we get to here. So next, what do we do? Right. So next, our goal is to then say, well, how about if I have some other number that I want to compute? What do I do in that case? Okay, here to get more palatable formula, I'm just going to look at the more general setting instead. Okay, what is the more general setting? So rather than just look at finite degree polynomials, which are very rarely occur in practice, we're just going to look at the full functions instead. So we're going to just look at arbitrary functions of a complex variable z, but we want these functions to be looking like polynomials. Okay, we want them to look and behave like polynomials of z. So this is in mathematics, this is usually captured by the notion of analyticity. So we're going to write down over here. See, notice that the only thing that we really can do is compute powers, and we only deal with polynomials. So one could say, well, what happens if I just only look at functions that are defined to infinite degree polynomials? So we can say, well, I'll give you a function f of z that is some of this form. Okay, I give you some center C. Let's not pick C. Let's call this as alpha maybe. Z minus C. Okay, so you would normally call this a Taylor series, right? If n went from 0 to infinity, you would call this as Taylor series. So just to set up everything, so we are in the complex plane, right? Normally you would call this the real axis, the imaginary axis, and C is some point we pick the complex plane, and then usually in our head, because it's a power series, there is some circle where this sum is going to converge. Okay, if this sum goes out this way to minus infinity, then you may have to cut out an annulus like that too. Okay, there'll be some annulus around C where this guy converges. Okay, in this class, because we don't want to like doing this definition through power series is like a tedious calculation. Okay, the only reason I'm doing it this way is because most of you don't know about Cauchy integral representation, so we won't do it that way. So this class, to keep our question thing more amenable to this tedious calculation to be something more thing, we'll assume that there are no negative powers of n, though of course the theory also extends when there are negative powers of n too. We'll just look at only Taylor series expansion. If you do allow negative powers, you should call it a Lorentz series instead. Okay, and we're assuming there's some radius r, so as long as you pick a z inside it, this sum converges absolutely. Okay, so inside, as long as z minus c is less than r, value of alpha n, absolute value of z minus c part of n is equal to infinity. Okay, so that's all the sums thing. So when a power series behaves like this, we say that it's an analytic function and it's got lots and lots of nice properties. Okay, you'll be a little bit careful when you work over this. Okay, this looks like analysis mumbo jumbo if you don't pay attention to the algebra. Right? Just like in any part of mathematics, most of the hard work is on the algebraic side, not on the analysis side. So here, the secret sauce of why we work with this is what else could I have written that I did not write down? Is the question, right? Of course, I could have used terms that were not powers, but that doesn't help me because I don't know how to compute 8th part of n. I don't know how to compute other functions of a anyway, so I'm stuck with powers. Okay, so I'm sort of stuck with powers. However, there is some other thing that we could have written down that we could try to force the meaning on, which is we could have had terms of the form z conjugate minus, say, c to the power of n2. We could have had that too. All right. Unfortunately, what happens is that if you allow functions that depend both on z and z conjugate, then those functions don't behave well, and the calculations become much harder. Okay, so you have to pick your point. Either you pick only functions that depend upon z, or only functions that depend upon z bar. You can't pick both. If you pick both, you get arbitrary functions in R2, and they are a nightmare to deal with. Okay, and we'll point out a few things about them as we go along. Really complex analysis is about this algebraic trick that you're looking at functions that somehow avoid certain linear combinations of the real and imaginary part of z. Okay, so again, this is not a class for complex analysis, so you should take a proper class. But unfortunately, the way complex analysis is taught, the algebraic part is sort of lost in it. Okay, you just learn some tricks. But anyway, that's something for another day. So these are called power series in Z, and in the region of convergence, these functions are very, very special. Okay, inside this region where the sum is converging, the graph of this function is very, very peculiar. Okay, it cannot be arbitrary, right? Notice that. So for example, inside the region of convergence, if I tell you this function at just countably many points, I just pick some dots, they're countably many, then the value of the function at countably many positions completely determines the graph in the entire circle. Okay, this is sort of like a version of the Shannon sampling theorem. Right, so the way people say is that complex analytic functions are very rigid functions. If you know them, so I take a tiny circle, take a very tiny circle, and I find countably many points inside this. Once I know the function at those countably many points, then I know the function everywhere in this thing too. Okay, it is extremely rigid. So because of that, it is actually a pain in the neck to work with this in real life, right? Because it's very intolerant of errors, this representation. Right, so in practice, you should never compute with these guys. Okay, they don't behave well, but theoretically, because they're so rigid, they're very easy to work with. Right. In this class, I'll barely touch upon these aspects, but it's important about why we go to complex analysis for some of our calculations. All right, so once we define this function, right? So for example, exponential of z, cos of z, sine of z, they all have representations like this: log, square root, cube root dot computation like this, right? And there are some nuances about this we will talk about later on. Okay, so once we have this, then you see that even though this is going up to infinity, it makes sense to ask what is f of a, right? If I now say these are complex, then I can say that f of a should be n equal to 0 to infinity, alpha n a minus ci to the power of n. Right, we could make this definition. However, there are some headaches with this definition too. Okay, it turns out that, for example, if I have some function f, say log z in mind, and I have a power series in some part of the domain, the power series will stop converging when it hits the first pole where the function blows up in some way. Okay, so it'll stop over there. So say the example is a pole over here. It'll stop converging when you hit that radius. But now if I pick another and I find another power series expansion for log z, you'll be able to do it still. Okay? But this power series will extend now all the way until hit touches it. So you've extended the log z from here to there. Alright? But it's a different power series now. It's not the one that you started with, it's a different one. It's the same function, but it's a different power series. Right? So it's not clear when you talk about f of a, which power series should I use? The one corresponding to this, the one corresponding to that, which one should I pick? Right? So when we approach the subject through power series, we have this unfortunate side effect that we don't know whether this definition is well defined or not. If I pick a slightly different power series, maybe it'll come up with a different meaning of exponential of the function. Right? It happens to not be true, but it's not clear at this point whether it is true or false. Alright, so to answer questions like this and make sure that you're talking about meaningful things, you have to go to the full complex analysis shenanigans. Either talk a lot more about power series or use the Cauchy integral formula, which is the same thing as saying talk a lot more about power series, unfortunately. So in this class, I'll be sort of cavalier about this, but I also want to say a few more words. So even the Taylor series expansions are nice, it's easy to use. You know, most of the time for engineering, when you say e power a, that's the only thing that they're thinking about anyway. So it's not a big loss. However, it is not the only way to talk about functions of matrices. Okay, so there's no such thing as a theory of functions of matrices. So for example, suppose I look at this nonlinear equation instead. Let's say that I want to find a square matrix A whose numbers I don't know, whose cube is this matrix 2, 3, 4, 5. Right? So this is a nonlinear equation. So there are 4 numbers inside this matrix A. I don't know them, but they satisfy 4 nonlinear equations. Right? So unfortunately, these kind of systems of polynomial equations are terribly difficult to deal with. So most people don't even know how to do anything about it. But let's set that aside. In this case, it looks like all we have to do is say, okay, let me call this matrix as A, and the right hand side is B, and then hopefully the solution of this is A is equal to just the cube root of B, right? That's what we would like. We would like to say that. So if I can find a power series expansion for the cube root function, if I can say P of f of x is equal to cube root x, and I can write this as summation alpha n x minus c, then I would have a systematic way of computing the cube root. Right? In fact, one might even be tempted to say, and this is the part where I want to warn you, that in fact I've seen many theses actually claim that those are the only solutions of this equation. Okay, because they use a complex analysis way of defining cube root. That is unfortunately completely false. Okay, there are many more solutions of this equation than you can get by complex analysis technique. Even if you were using Cauchy integral representation, it doesn't matter. Okay, so when you use functions of matrices to solve nonlinear equations, be super careful. Huh? They cannot see all the solutions. They only see a portion of the solutions. So this functions of matrix approach has some validity, and I think mostly, I would say, controls people tend to lean on it more than other people, but it's not the whole game. Okay, they're solving nonlinear equations using this method. There are other solutions too. Okay, so especially when you work with nonlinear problems, be a little bit careful. Counting is extremely difficult. There's no systematic way to do it. All right, so our job then is to stick. So with all the caveats in place, we just need to find this, right? But it's still a polynomial, so we can see what to do. So we see that A minus Ci written as Vj V inverse minus Ci, which can be written as Vj minus Ci inverse V inverse, like that. All right, so therefore f of A minus Ci, f of A, will be just V f of j V inverse, just like before. Okay, none of those things will change. Right, so we just have to worry about computing the function on the Jordan form itself, and when we stick it f of j in, because of this expression on the top, you'll only get things like this, alpha n j minus ci to the power of n. This is the only thing that we have to worry about. Okay, so in the next class, which is not next week but after Thanksgiving break, we will start our computation from here and show, given a power series representation for the function we care about, how to evaluate that power series at a certain Jordan, at a single Jordan block, and what that representation looks like. Okay, and then after that, we will stop with functions of matrices, and we'll go back to talking about how to find the eigenvalues of a matrix when you don't know too much about the matrix. Okay, and we'll talk about symmetric matrices in that case. All right, that'll be all for today.